Hi everyone, Mrs. Hanson here. We're beginning chapter 7 today, looking at alkyl halides and nucleophilic substitution reactions and elimination reactions. In our first lesson today, we are going to investigate kind of what is an alkyl halide. Our topic today will be substitution reactions and elimination reactions and nomenclature practice with alkyl halides. We'll begin investigating an SN2, a nucleophilic substitution bimolecular reaction. And we'll investigate how we influence the kinetics, the rate of that nucleophilic substitution reaction, by investigating the strength of the nucleophile and the solvent effects for SN2. In the next lesson, I'm going to assign reading for this chapter in section 5. Lesson 2 will begin investigating E2, elimination reactions that are bimolecular. We'll talk about the nomenclature of alkenes and the stability of an alkene. We'll look at the regioselectivity and the stereoselectivity for outcomes of E2 reactions. So in our next topic, we'll investigate SN2 to begin with. Then we'll move our attention to E2 reactions. And then finally look at some opportunities to talk about unimolecular. SN1, nucleophilic substitution, that's a unimolecular, and elimination that is a unimolecular in terms of their rate limiting step. So kinetics and equilibrium will come out to play here towards the end. And when we try to predict the outcome of substitution versus elimination, we think about both the thermodynamics and the kinetics that would promote one mechanism over the next. We'll also take a quick peek at substitution and elimination with other substrates. Instead of just using an alkyl halide, what if we started with a sulfur, for instance? And then ultimately, we're going to look at synthesis strategies, planning a synthesis, select a reagent, select a starting reactant to produce a desired product. So this is a big chapter. We actually have 4 days devoted to this section, and I'm kind of looking at breaking them up into small lessons best we can, but give yourself plenty of opportunity to practice. Chapter 7 truly is the first time that we are investigating mechanisms in the outcomes of competing chemical pathways. So let's dive in and talk about our alkyl halides and just make sure we understand what it is we're studying in section 7.1. Title of our chapter was alkyl halides. So let's make sure we understand its definition. An alkyl halide is defined as a reaction that will undergo substitution and elimination reaction. So again, those two competing pathways, substitution and elimination, they only occur in an alkyl halide. So how do we recognize an alkyl halide? Notice here we have a carbon that's attached to a halogen, and notice that X is going to represent an alkyl halide. X can be the halogen of chlorine, bromine, and iodine. Notice how I'm leaving off fluorine because fluorine really doesn't have a very good leaving group, very good success rate. So a halogen that's more successful is chlorine, then bromine, then iodine. Notice that we have an sp3 hybridized carbon. That carbon is attached to 4 unique atoms. sp3 hybridized means that it is tetrahedral in terms of molecular geometry. This classification, this carbon is also attached to a halogen, but notice that carbon is in an aromatic compound. This is what we refer to as an aryl halide. And then if the carbon directly attached to the halogen is in a double bond, we'll learn that this is called a vinyl halide. And both of those are studied, but they're thrown ahead into their own chapter. Chapter 23, when you look at aryl halides and vinyl halides and their chemistry. This chapter is devoted to the sp3 hybridized carbon, where one of the 4 attachments leads you to a halogen. So an alkyl halide, Rx, right, where the R is sp3 hybridized, and the halogen, chlorine, bromine, or iodine, and I know fluorine is a halogen as well. And the reactions they undergo are called substitution and elimination reactions. So these nucleophilic substitution reactions, you see those abbreviated as SN1 or SN2 in terms of their mechanisms. So SN, nucleophilic substitution reactions. Nucleophilic substitution reactions are those in which we will see a nucleophile replacing the halogen. So in our substitution reaction, notice here we have 1, 2, 3 carbons, 1, 2, 3 carbons, and then attached to it would be some halogen. So just kind of think about 1 chloropropane, for example, right? 1 chloropropane. And we have a nucleophile who has a set of lone pair electrons, and what's happening is it's seeking a electrophile. And we talked about this in last chapter in terms of, how to draw mechanisms, how to draw proper arrows, that the arrow will originate at the electron-rich nucleophile, and it's going to attack an electron-deficient carbon based on the polarity of that bond. So this carbon here is an electrophilic carbon because its electron density is being pulled away from it towards the halogen. So this is a very electron-rich area. This is a very electron-deficient area. And when we see that, we'll notice that the nucleophile kicks out the leaving group, and we will define the leaving group as the halogen. It picks up its electrons and leaves. And so notice that we've just substituted the nucleophile in the same position as the original halogen, and we will definitely talk about mechanism every single time we do this. So the nucleophile and the halogen have exchanged places. It's a substitution reaction. We will then spend time looking at elimination reactions in very much detail. Here we're just kind of throwing out what we're coming up to study, but this is kind of where it's heading. An elimination reaction, we see that we have a halogen present, but we also, let me kind of highlight this, we're also going to be looking at the beta hydrogen, which will be attached right here. So even though we don't see them, we know that there are hydrogens attached to that particular carbon. So the hydrogen and the X are going to be leaving. And so an elimination is thinking about minus HX, where the base is going to take off a proton. The halogen is then leaving, and then the bond collapses, and we end up with an ene, a double bond. That's what we're studying, and I'm just putting out there for the first time, substitution and elimination reactions are the two most common types of reactions alkyl halides undergo. Under substitution, we have two different mechanisms that can occur. We need to investigate SN1, nucleophilic substitution unimolecular, and an SN2, nucleophilic substitution bimolecular. And this has to do with the kinetics. And again, remember we spent a little time talking about kinetics in last chapter, the rate of a chemical reaction. Well, that rate has to do with the rate determining step. If the rate determining step relies on just one molecule, it's unimolecular. If the rate determining step relies on two molecules, you called it bimolecular. So the collision of two molecules in the mechanism, SN2. The unimolecular relies on a single molecule rearranging. And the same is down here for elimination. We'll see a E1 and an E2 mechanism. Both really just produce the same thing. We'll end up with a pi bond, but it's how they get there that's different. So the mechanisms are very different. The outcomes are the same. Alkyl halides undergo two reactions, nucleophilic substitutions. Those are in two categories, SN1 and SN2, really just depending upon their pathway. And elimination reactions form that double bond when treated with a base. We need to also highlight, just making sure we see what's on the arrow. A nucleophile promotes substitution. A base promotes elimination. We need to spend time making sure we understand the difference between when a compound will act as a nucleophile and when a compound will act as a base. Here's a nice graphic to give us insight of where we're heading. In the kitty cat cartoon, if you will, this represents substitution reactions, SN1 and SN2, a substitution reaction. Notice that we have what we refer to here as our substrate. This gray kitty cat is laying in the bed, and this is our attacking molecule we'll call the nucleophile. Now, the substrate in this unimolecular mechanism, this kitty cat, this orange, he is just sitting there waiting for the bed. He cannot get in the bed until the orange kitty cat leaves. So the leaving group leaves all by itself. Nothing forced it to leave. Leaving group leaves all by itself. Then when the bed is empty, the orange kitty cat can come in. A unimolecular. This reaction relied on the rate, the rate determining step, relied on one kitty cat, and that was the gray kitty cat, and that was simply waiting for it to leave. Compare that to a bimolecular reaction. We have the same setup. Here is your substrate, your alkyl halide. Here is your nucleophile, and we have the same beginning picture. Gray kitty cat in the bed, orange kitty cat would like the bed. But instead of just waiting until the gray cat gets up and leaves, unimolecular, the leaving group leaves all on its own. Bimolecular, we have two cats colliding. That instead of just waiting around, the orange kitty cat kicks out the leaving group, and the leaving group left because it was forced to. A bimolecular has a collision between two molecules, a collision that forced the leaving group to leave. Whereas a unimolecular means that one molecule was involved in the rate determining step. One molecule, while we waited for that gray kitty cat to leave, as long as it wanted to lay there, the reaction would not proceed. With a bimolecular, two molecules collide and the leaving group is forced out. So substitution reactions, kind of in general, one kitty cat replaced the other. One substrate replaces the alkyl halide. Now down here, and just kind of bringing this into sense, we have eliminations in our chapter as well. Elimination reactions. We need to decide if an elimination, remember, is when we minus an HX and end up making a pi bond. Part of our investigation is to decide, would we promote substitution or do we promote elimination? Because they're actually competing pathways. And there's a lot of factors you have to consider in answering that. And we'll talk about those one at a time. But the strength of the nucleophile, the solvent you select, the ability of the leaving group to leave, and even the temperature that you run the reaction at all influence the rate of substitution or elimination. So let's define the term substrate. I said it a lot in that last slide. The substrate we're focusing on in this chapter is an alkyl halide. That's our title of chapter 7. We said the alkyl halide must have an sp3 hybridized carbon, that the tetrahedral shape is a requirement. When a reagent can act as a nucleophile or a base, elimination and substitution reactions will compete with one another. So here we have sodium hydroxide, sodium of course being the spectator ion. Hydroxide, will it react, and kind of just thinking that through, if it acts as a nucleophile, we will promote substitution, nucleophilic substitution. But if the hydroxide acts as a base, it will promote elimination. And let's think about really what we're saying there. We have a 2-chloropropane. And notice this is now called my substrate. This is what we're referring to as our substrate. It's the alkyl halide, right? And so then the nucleophile, if indeed the hydroxide is going to act as a nucleophile, and it may sit on top of the arrow, or it could be just, written as a next reactant, either on the arrow or as a reactant. Notice this carbon right here is a very positive carbon based on the electron density being pulled towards the chlorine. So as we'll investigate, our arrow originates on the set of electrons here in the rich nucleophile. And so it would attack the carbon that's a positive. So the nucleophile is seeking the electrophile, and that's the carbon. The leaving group then leaves, and it picks up its electrons and does so. So when this happens, we can see that an OH group formed, and so a substitution, and notice the chloride as it, picked up its electrons and left. And that's exactly where the sodium then would migrate to balance the electrical charge. So the sodium is present just as a spectator to balance charge. So when this substitution occurs, we're looking at that as calling it a nucleophile. And a nucleophile, again, two different methods of getting there. And I'm just saying you have the same outcome. I don't care if it was a unimolecular or a bimolecular pathway. The substitution would occur when the chloride leaves because the hydroxide took its place. Alrighty. Now, what if we called it, and just kind of considering the same compound, here's that 2-chloropropane, but now all of a sudden I call this a base. And over here are those hydrogens. Alrighty. So now as a base, we're looking at a different mechanism. The base, instead of going for the electrophilic carbon, the base, we understand, transfers a proton. Alrighty. And that proton is plucked off, and it leaves the electrons. These two pairs of, not two pair, but two electrons in the shared pair are left. Then, of course, the leaving group leaves, and it takes its chloride electrons with it. So again, you would end up with a chloride ion. The leaving group leaves. I'll just put the Lg so you can see what I'm referring to. The leaving group leaves, meaning that the sodium will migrate over there just to balance the charges. And since the chloride left, these set of electrons, they're going to collapse and form a pi bond. The original shared pair that we're holding the proton on collapse to make a double bond. And then, of course, we'd see the other product, the HOH, the water molecule form. So in the elimination reaction, we form propene. In the substitution reaction, we made 2-propanol, the alcohol. So notice we had an alkyl halide turn its functional group just changed completely into an alcohol. And down here we started with an ane, 2-chloropropane, and turned it into an ene, propene. An elimination versus a substitution. This really is the in-depth look at what we're studying. How do we promote substitution over elimination? How do we select a solvent? How do we select the proper nucleophile? How do we select a base if we want to have it as an elimination? And we'll even consider temperature as another reaction condition to promote elimination over substitution. So there's two main reasons why an alkyl halide will undergo substitution and elimination reactions. And we alluded to those in our previous slide. Number one, the halogen that's on the carbon chain is a very inductive electron withdrawing species. So it creates an alpha carbon that's very positive. So just thinking about this structure here, an alkyl halide, based on the electronegativity difference to some halogen, the bond itself is very polar, that the inductive effect is taking the electron density away from the carbon and pulling it to the halogen region. And this is just kind of a graphic that I pulled to add to this, that you can see here's a fluoride in this alkyl halide here, CH3F. So here's the fluoride. A little bit bigger is the chloride, a little bit bigger is a bromide, and then finally you have methyl iodide. But there is definitely a region that's electron rich and electron deficient. The purpose of this graphic is to show you how positively charged the carbon is, making it a very nice target for a nucleophile. Nucleophiles seek positive charges. Based on the electronegativity difference of that polar bond, the carbon becomes electrophilic. And the second reason that alkyl halides undergo substitution and elimination reactions is that the halogens are really good leaving groups. They can stabilize a negative charge. Fluoride, not so much, but fluoride is so tiny it has a hard time stabilizing with its small surface area, so it's not a very good leaving group. And over here, chloride's a little bigger, bromide's a little bigger, and iodide with its large polarizable squishy cloud is a very good leaving group because it can stabilize the negative charge over a large surface area. So halogens are good leaving groups, and the halogen itself creates a nice positive target for the nucleophile to attack. And that's the two major reasons why the alkyl halides undergo substitution and elimination. I mentioned the what makes a good leaving group. Well, a good leaving group has the ability to stabilize a negative charge. Good leaving groups stabilize negative charges very well. Kind of remembering back in chapter 3 when we did acid-base chemistry, we said a weak conjugate base of a strong acid is a very good, good at stabilizing its charge. So good leaving groups are very good at stabilizing negative charge, and that's exactly what we said conjugate bases of strong acids do. So the more stable the structure, the better it is at creating an opportunity to stabilize that negative charge. That's going to create a good leaving group. So here's a rule of thumb. A good leaving group is the conjugate base of a strong acid strong acids, typically, if you just kind of look at about here, if you have a pKa on an acid that's below 0, hydronium, the sulfate, hydrogen chloride, hydrogen bromide, hydrogen iodide, all have pKa's that are below 0. Their conjugate bases then are very good leaving groups. And so just to kind of put that in perspective, if you have an alkyl halide, and that halide is iodine, it's a very good leaving group because I negative can stabilize its charge. So it's very likely to pick up those electrons and just leave. By the time I'm down here and I were to have a nitrogen, this is not a very good leaving group because the NH2 negative has a very difficult time stabilizing that extra formal charge of -1. Oxygens, poor leaving groups. Nitrogens, poor leaving groups. Plus they're kind of small, aren't they? They're not very ionizable. So the strong acid of HI forms a conjugate base of I negative. This is a very large polarizable cloud and therefore can stabilize the negative charge quite well. The conjugate base of very strong acids are great leaving groups. In our next section, we investigate alkyl halides and really just kind of practice naming some as well. Let's return to some vocabulary here as I'm looking over the structure. In the first picture here, I notice the carbon that's directly attached to the halogen. And that carbon directly attached to the halogen is known as the alpha carbon. So the carbon atom connected directly to the halogen is called alpha. When you go out in either direction, the beta carbons are then attached to the alpha. And if you go out even one further, you have gamma, and if you go out even one further, you would have delta. But in our case, we're really only going to look at the alpha and the beta position of alkyl halides. So if I'm looking at a structure and I notice that, let's say it's even got a methyl, that's one carbon, that didn't come out very well. Let me redraw to be neat. Let's do 1, 2, 3, 4. I don't care. There's a lot of zigzags. I'll put a methyl here and a bromine. Alrighty. So here is the carbon that's attached to the halogen. So that would be an alpha carbon. I then notice that I have one adjacent carbon there. That's beta. I have one adjacent carbon there. That's beta. And I have one adjacent carbon there. That would also be beta. You'll notice that if the alpha carbon is attached to just one other carbon, it's called primary. If the carbon that's alpha is attached to two other carbons, it's called secondary. And if the carbon attached to the halogen, which is alpha, is attached to three other carbons, it's called tertiary. And we'll see that this has no opportunity for elimination reactions because there's no hydrogen in the beta position. And so that's one of the requirements we'll learn. If I'm going to remove an H from the beta position, it has to have one there, and a tertiary alkyl halide does not. When we think about naming alkyl halides, all of the same rules apply as before when we were naming alkanes. Alkyl halides are simply carbons or compounds that have carbon groups bonded to fluorine, chlorine, bromine, or iodine. So all of the steps we practiced back in chapter 4, identifying and naming the parent chain, giving the name of the substituents and assigning a number to those substituents, and then just assembling those pieces alphabetically. Remind yourself that it does matter which direction from the carbon chain you order, making sure that the substituents get the lowest possible number. In this case, it absolutely did not matter if I numbered left to right or right to left. I still come out with 2-chloropropane. However, in this example, if I numbered right to left instead of left to right, I would have had 4, 4 instead of 2, 2. The lower number wins. And then we alphabetize. So 2-bromo, 2-methylpentane lists those substituents with the lowest possible number, as well as alphabetically. And then down here, recall, again, just making sure you see why we're numbering left to right. 1, 2, 3, 4, 5, 6, 7 carbons in the longest carbon chain. When I numbered left to right, the first branch was at carbon 2, the second substituents are at carbon 3, and the final branch was at 5, 2, 3, 3, 5. However, if I were to number in the opposite direction, notice that the first substituent then is at carbon 3, and that doesn't work because 2 is smaller than 3. So that's why we're numbering this direction. Also recall that you alphabetize. There is your B, 5-bromo. We had 3 groups of methyl at carbon 2, 3, 3. And then this is a chiral center. So the chiral center has to be named in there as well. At carbon number 5, we had a stereocenter. It was spinning in the clockwise position. Bromine would be priority number 1. Priority number 2 would be the carbon leading to more carbon. Priority number 3 would be the carbon leading to less carbon. And of course, not shown, but we know is there, is the dashes for the hydrogen. And when I spin that, I came out with a clockwise rotation, so that's your R configuration. Let's practice. Pause your video and draw these, giving them a name. Practice, practice, practice. Pause the video, draw, name them, and then come back. All right, well, let's see if we came up with some common answers. I know this has to be carbon 1, 2, 3, 4, 5. Numbering right to left gave me a position of 1 chloro, gave me a position of 4, 4 dibromo. What if I numbered left to right? 1, 2, 3, 4, 5. I would have had 2, 2 dibromo and 5 chloro. So the first point of difference obviously is right here. 1 is a lower number than 2, so this wins. There is no stereocenter. I don't see a chiral carbon to have to worry about in letter A, so let's just name those branches. We had a 5-carbon chain, so that will be the parent name will be pentane. At carbon number 1 was a chloro, carbon 4, 4 is bromo. Now remember, we alphabetize. So 4, 4 dibromo. That alphabetizes with the B, and then I'll let you know at position 1 was the chloro, and then when a 5-carbon chain called pentane. 4, 4 dibromo, 1 chloropentane. How about letter B? Well, in a cyclic structure, looks like we had a 6-membered ring. At carbon number 1, we had a bromo, and at carbon number 1, there is a methyl. And I'm going to alphabetize those. And I don't see any stereocenters there, so I don't have to worry about an R or an S. How about letter C? Well, let's see. I'm going to number 1, 2, 3, 4, 5, 6, 7, 8. Let me just test the other direction. 1, 2, 3, 4, 5. So that's not right. We have the lower number when I ordered from left or from right to left. So that's where I'm going to just renumber to clear up. 1, 2, 3, 4, 5, 6, 7, 8. All right. At carbon number 4, that looks like a stereocenter. So that's got to be part of the name. The longest parent chain looks like an octane, so that will be the last name, octane. And I can see at carbon 4, there is a chloro and an ethyl. So chloro comes before ethyl. And, yep, it's still carbon 4. And this is all one word, so that might be misleading. I still need to tell you the stereochemistry of that chiral carbon. So let's see what we have. We have top priority would be the wedge. That's nice. Then we would have second priority would be the carbon leading out to most carbon. Then that's 1, 2, 3, 4 carbons in that direction, where this is just 3 carbons in that direction. So that's of third priority. And of course, the lowest priority is in the back. So that's nice. This is spinning in a clockwise fashion. So that is an R configuration. How'd you do? Oh, there's more for you to practice in homework, but at least you got a chance to practice with me. There are some simple molecules to recognize by common names in addition to the IUPAC name. The systematic name for existence, the IUPAC name, is to just say, like for a 2-carbon chain, This would be chloroethane. Notice you do not need a 1-chloroethane because it's the same compound if I put chlorine on the first carbon or it becomes the first carbon either direction. So I don't need the 1. IUPAC is chloroethane, or a common name you might hear just simply called ethyl chloride. Here's another example. An IUPAC name, systematic name, would be so we'd call that dichloromethane, but you might also call it methylene chloride. Methylene chloride, see how there's just one carbon there? And oftentimes chemists in the lab will use methylene chloride as a common solvent. So just think about what that looks like. You've got 2 H's and 2 Cl's on a carbon. That's called methylene chloride or dichloromethane. Well, let's dive into these nucleophilic substitution reactions. A substitution reaction that requires the loss of a leaving group and a nucleophilic attack. There are 2 possible mechanisms in a nucleophilic substitution: a concerted, which is bimolecular, 2 molecules colliding at the same time, or a stepwise, which is unimolecular, which the leaving group has to leave and then the nucleophile arrives. So step 1, the leaving group leaves. Step 2, the nucleophile arrives. I'm just thinking back to the kitty cats. Bimolecular is a concerted effort because the 2 cats collide, 2 molecules collide, and off they go. So a concerted mechanism involves breaking bonds and forming new bonds all at the same time. And that's what I'm going to study here first. We'll do SN2 bimolecular as a first investigation, and then later on we'll come back and investigate a unimolecular, which is a stepwise mechanism. We just got to start somewhere. Let's focus on SN2 first. Nucleophilic substitution reactions bimolecular. So the concerted mechanism involves breaking the bond of the leaving group and making the bond of the nucleophile at the same time. Now think about the cats. The 2 cats collide, forced one out of the bed, so the other one stole it. At the same time, we will have a nucleophile attack the electrophilic carbon, forcing the leaving group to leave. Substitution means where used to be a halogen, there is now a nucleophile. The 2 electrons that are in this covalent bond, both are taken by the halogen. So the leaving group takes the electrons in that bond. But that's all right because the nucleophile is bringing a pair of electrons to form the new bond. Notice that this will have a transition, kind of like a transition state, where bonds are breaking and new bonds are forming. And let's investigate that as well. So the stepwise mechanism, the leaving group leaves first to give a carbocation intermediate, followed by a nucleophilic attack. That is what I'm referring to as an SN1 unimolecular, where we have the leaving group leaves, we have an intermediate form, and that intermediate is going to be an sp2 carbocation. It's going to have an electron deficient carbon, so it's a carbocation. And then in a next step, the nucleophile attaches to the carbon that's electron deficient. So notice we have a step 1, the leaving group leaves. Step 2, the nucleophile attacks. Since it's a stepwise mechanism where the rate determining step in terms of kinetics is just waiting for the leaving group to leave. That's why it's known as a unimolecular mechanism. The rate determining step involves just one molecule. We're going to come back to that in section 10, but we have a bimolecular, focus on first. We'll come back with a unimolecular a little bit later. So what does S and N and 2, what does that all stand for? How might you write a rate law for this stuff? And what would you design in terms of a laboratory experiment to confirm this rate law? Let's kind of take each one of those questions at a time. The S stands for substitution. The N stands for nucleophile. And the 2 means that it's a bimolecular rate determining step. The slowest step in the mechanism involves the collision of 2 molecules. Nucleophilic substitution bimolecular. That's what we have to envision SN2 standing for. So if the rate determining step involves both the nucleophile and the substrate, the rate then could be written by saying rate is equal to K, that's the rate law constant, times the concentration of the nucleophile to the first order, times the concentration of the substrate to the first order, and that would be second order overall. So there's your kinetics for a bimolecular reaction. First order with respect to the nucleophile, it will influence the rate of a reaction. First order with respect to the substrate, it will influence the rate of the reaction, and it will be second order overall. How would you design a laboratory experiment to confirm that? Well, this is where you used initial rate law data, and you would take initial rates and vary the concentrations of each of the reactants. So for example, if you take the nucleophile, for instance, and you doubled the concentration, you would expect the rate to also double. That's a first order overall, right? The first order, what you do to the nucleophile, the reaction rate follows directly. Doubling the amount of nucleophile would double the rate. The same is true for the alkyl halide that we called the substrate. The substrate is first order, so if you doubled the concentration of the substrate, you would also expect the rate to double. And if you end up doubling both, the rate would actually quadruple. So that's investigating the kinetics of our reaction. A bimolecular, so the collision says, here we have this electron-rich area on the nucleophile, and it seeks out the electrophile carbon. Remember, this is very polar, making the carbon positive. And so that's the first step, is that nucleophile attacks that electrophilic carbon. That makes the leaving group leave. Both of these electrons go with the leaving group, and that's how now the halogen has a -1 formal charge. And there's a new bond that forms from the electrons that were originally with the nucleophile. So the new bond that forms, there's just one new bond forms from the set of electrons. A simultaneous collision. So here we have a transition state. So as the nucleophile reacts with the substrate, just to kind of remember, a transition state with this symbol here then goes on to form the actual product. And so you would end up having your leaving group and your new alkyl, whatever that would be, the carbon with the nucleophile on it now. So thinking about a transition state, what does that look like for this kinetics? Well, that's where we have bonds breaking, new bonds forming, and just kind of thinking about those dashed lines. Here is the process where the halogen bonds are breaking. Here is the process where the nucleophile has bonds forming. And of course, you still have the R, the H, and the H. Those other 3 bonds are still present. But that transition state, let me label that with a vocabulary word. It shows that there's no intermediate, but just one transition state for this mechanism. Thinking about its thermodynamics, you'd have an initial reactant, one energy barrier, and going on to form product. Right up here is the transition state where bonds are breaking and new bonds are forming. SN2, bimolecular, is a concerted mechanism. Concerted mechanism means one step. Bimolecular means two molecules collide. And that's the overall rate law. Rate is equal to K times the concentration of the nucleophile to the first order times the concentration of the alkyl halide. I'll just call that our substrate. Or we can even put, how about Rx, so we can remember what the substrate actually is. The alkyl halide is our substrate, and that's first order. And so you would call that second order overall. And the energy diagram would have initial reactants, one energy barrier, forming products. And your transition state is at the top of that barrier. This requirement here is called activation energy. So let's consider that as we look at the following reaction. The following reaction is second order kinetics. Second order kinetics. So that rate law means rate is equal to K times the concentration of 1 propane first order times the concentration of sodium hydroxide, which sodium we know to be a spectator, so it's really not involved in the reaction, and that would be first order. So that's what we mean by a second order kinetics. It's first order with respect to the alkyl halide, first order with respect to the nucleophile, and second order overall. What would happen to the concentration, what would happen to the rate if the concentration of our alkyl halide, you're right, I forgot to name the iodine here, 1 propane, 1 what? 1 iodopropane. If we took 1 iodopropane and you tripled it, and the sodium hydroxide remained the same. Well, since it's first order with respect to the alkyl halide, the rate would also triple. If the rate changes, if what happens to the rate if the concentration of 1 iodo remains the same, but now you're going to take sodium hydroxide and double it? Well, they're both first order, so the rate would also double. Whatever you do to the concentration of either reactant, the rate will follow directly. What happens if you double the concentration of iodopropane and the concentration of sodium hydroxide is tripled? Well, let's figure that out. If you double the concentration of the alkyl halide, the rate will double. So from 1 iodopropane, we doubled it, so the rate will double. The sodium hydroxide was actually tripled. And if you triple it, the rate will triple. So overall, it's going to go 6 times faster. It's like thinking rate is equal to K, 2 to the first order, 3 to the first order, their first order overall right there. So that ends up to be 6 times faster. Little kinetics review. How does the observed stereochemistry in the following reactions support an SN2 mechanism? This is a great pausing point. I'm going to come back and talk about stereochemistry and its consideration in terms of chiral centers in our next lesson. We've been going about 50 minutes. Let's pause, take a break, and then come back when ready, and we'll pick up this lesson there.